Welcome to a new frontier in gravitational physics, Macroscopic Casimir Gravity, or MCG. This theoretical framework challenges the classic view of gravity as merely the curvature of spacetime, as described by Einstein's general relativity. Instead, MCG proposes that gravity emerges from both spacetime curvature and a macroscopic vacuum energy flow field, denoted as Cμu. In this video, we'll explore the key ideas, motivations, and experimental proposals behind this bold new approach, and see how it could reshape our understanding of the universe. To appreciate MCG, let's briefly revisit the evolution of gravitational theory. Newton first described gravity as a force acting at a distance, encapsulated in his famous equation. Centuries later, Einstein revolutionized our view by showing that gravity is the manifestation of spacetime curvature, governed by his field equations. Now, MCG builds on these foundations, introducing the idea that gravity also involves a vacuum energy flow, adding a new layer to our understanding. This historical progression sets the stage for the innovations of MCG. General relativity has been remarkably successful, but it leaves some puzzles unresolved. For instance, it doesn't fully explain why gravity might behave differently for various elements or how density could affect time dilation. Additionally, the role of vacuum energy, demonstrated by Casimer physics to be geometry-dependent, remains mysterious at macroscopic scales. MCG is motivated by these gaps, aiming to extend our grasp of gravity by incorporating the effects of vacuum energy flows. At the heart of MCG are three main ingredients: a vacuum flow field Cμu, a flow matter coupling parameter alpha, and a master scalar Xi that regulates time and inertia. These elements work together to produce observable effects that go beyond what general relativity predicts. The framework is designed to reduce to Newtonian gravity and GR in familiar situations, but it also opens the door to entirely new phenomena, such as flow-regulated time dilation and tunable inertia. MCG's theoretical structure is built from several core fields. The metric Gμu describes spacetime geometry, just as in general relativity. The vacuum flow 4-vector Cμx represents the new macroscopic energy flow. Matter fields, denoted psi, interact with this flow through a coupling scalar alpha that depends on atomic number, temperature, and density. Together, these fields define the dynamics and interactions that set MCG apart from previous theories. The mathematical backbone of MCG is its action, which integrates contributions from gravity, matter, vacuum flow, and their couplings. The action is written as an integral over spacetime, combining the familiar Einstein-Hilbert term with new Lagrangians for the flow and its coupling to matter. This unified approach ensures that the resulting field equations are consistent and capture the interplay between curvature and vacuum energy flow. MCG introduces two new Lagrangians, one for the vacuum flow field and another for its coupling to matter. The flow Lagrangian describes the dynamics of Cμu, including its mass and field strength. The coupling Lagrangian encodes how matter interacts with the flow, with the strength of this interaction determined by the scalar alpha. These additions enrich the theory, allowing for new physical effects that can be probed experimentally. With these new ingredients, the Einstein field equations are modified. The gravitational field now responds not only to matter, but also to the energy and momentum of the vacuum flow. This adjustment means that the geometry of spacetime is influenced by both traditional sources and the dynamics of Cμu, leading to potentially observable deviations from general relativity in certain regimes. Flow field Cμu itself obeys a new equation, balancing its own dynamics with the influence of matter. This equation involves derivatives of the flow field, its mass, and a source term that depends on the matter fields and the coupling scalar. The result is a rich interplay between matter and vacuum energy flow, with feedback effects that could manifest in experiments. One of the most intriguing predictions of MCG is that the passage of proper time can be regulated by the vacuum flow. The theory predicts that heavy elements, or those at high temperatures, experience stronger time drag effects due to their enhanced coupling to the flow. In certain conditions, neutral zones may arise where this effect vanishes. These predictions open new avenues for testing gravity using atomic clocks and engineered environments. MCG also predicts that inertia itself can be modulated by the direction and strength of the vacuum flow. Inward flows increase effective inertia, while opposed flows reduce it. This means that, in principle, engineered cavities could be used to tune the inertia of test masses, a phenomenon with profound implications for both fundamental physics and potential future technologies. The new dynamics introduced by MCG lead to several observable gravitational effects. These include density-dependent gravitational responses, element-dependent deviations in free fall, and anisotropic forces induced by the vacuum flow. Time drag gradients, in particular, could be measured with high-precision atomic clocks, providing a direct test of the theory's predictions. Test MCG. Researchers propose a series of atomic clock experiments. By comparing clocks based on different elements, such as hydrogen and ytterbium or mercury, and placing them inside or outside engineered Casimer cavities, scientists can look for the predicted time drag effects. Temperature-controlled environments add another layer of control, making these experiments a powerful probe of the theory. Another set of experiments focuses on measuring changes in effective inertia. Using torsion pendulums, oscillating cavity boundaries, and high atomic number test masses, researchers can search for the predicted modulation of inertia. These setups could reveal subtle effects that would be impossible to explain with general relativity alone. MCG also suggests that directional forces can be generated by manipulating vacuum flow gradients. Experimental methods include creating asymmetric cavity arrays, applying pulse boundary conditions, and designing flow lensing metasurfaces. These approaches aim to detect and control the new forces predicted by the theory, potentially opening the door to novel technologies. Space offers a unique environment to test MCG's predictions. Proposed experiments include measuring satellite clock drift in different cavity configurations, mapping flow gradients in microgravity, and conducting long baseline time drag measurements. These space-based tests could provide the most stringent constraints yet on the theory, leveraging the precision and isolation available in orbit. Macroscopic Casimir gravity represents a unified, mathematically consistent extension of general relativity. By incorporating vacuum flow dynamics, it predicts measurable deviations in time dilation, inertia, and gravitational behavior. With a range of proposed experiments, many using existing atomic clock and cavity technologies, MCG stands poised to be rigorously tested. If validated, it could mark the next major leap in our understanding of gravity, following in the footsteps of Newton and Einstein.